Good morning. Welcome back. Chemistry 1 Part 2 today. So we started looking last week. We looked at atomic structure. Sorry, last week, Monday. We looked at atomic structure. We looked at chemical reactions, and we some of the sort of basic definitions with atoms, with compounds, with mixtures. We sort of looked at atomic structure, and we looked at the periodic table, so that we could start having a look at sort of what the groups are, what the periods are, atomic mass, atomic number. We looked at how the structure of the atom has developed over time, and we looked at the sort of key people involved in that. Morning, Tanishka, good to see you online. We looked at the key people that are involved in that, and we looked at their, I suppose, the ideas, the theories that they contributed. Morning, Amy. And we also had a look at I suppose how science really develops as we make new discoveries. So there's loads of things that we're still investigating, we're still trying out, lots of experiments, lots of ideas, and that's really what science is about, isn't it? We sort of have an idea about something, we go, we test it, and we sort of change our views based on the evidence, really. So that's what we were looking at to start with. We looked at a few other definitions as well. We looked at isotopes, and we said that isotope was any atom with same number of protons, because we said the number of protons is what dictates the type of atom. But actually we can have any number of neutrons. There are some atoms which have a very standard number. So if we're looking at carbon, most carbon atoms have 6 neutrons. They all have 6 protons, or they wouldn't be carbon. But we can have some other isotopes as well. So about 1% will have 14 neutrons. Sorry, we'll have 8 neutrons rather than 6. So we looked at this sort of term isotopes. And where we finished is we started looking at electrons and electron configuration. So I think that's where I'm going to start today. So I want to drop in the periodic table again. So let's just go up to... So we'll start off with the periodic table, because actually what I want to make sure is that as we're going through this, everything we do, morning Olivia, everything we do is linked to the periodic table, because actually in order for you to do the best you can, you need to be constantly referring back to the periodic table. It shouldn't be something that's just sat with an exam paper or just sat in a book and not referred to. We can learn so much for it, and it's pretty much the stock thing as a chemist we always need to have accessible. We need to realise the information that we can get from it. We need to have a rough idea of where some of the atoms are. We don't need to memorise it, but we need to know sort of roughly where we're looking. So the more we look at it, the more familiar we get. But it's not something we have to learn. I mean, I know a lot of people go, oh yeah, I know the first sort of 20 elements off by this. Well, that's brilliant, but you don't need to, because it's something you will always be given in an exam. I don't know them. I'm comfortable with quite a few of them, but that's just because I've been doing this since, well, pretty much since I started secondary school. So I'd have been 12 at the time, and I'm sort of 39 now. So been doing this for quite a few years. Now, we looked at then, we said that the columns going down are the groups. Now, at the moment, we are only looking at the main groups. We are not looking at the transition elements. We said that each of the rows going across we will call a period, because at the end of the day it's the periodic table. So if we're numbering these, we start off with number 1 there, 2, 3, 4, 5, 6 and 7. There are some elements there. I know one of you last week was talking about Rutherfordium. And it's not shown on this periodic table, but it is shown on some periodic tables. But you need to have the lanthanides and the actinides for that to be shown. And they don't really sort of come up much in GCSE. They come up sometimes in physics, because most of them are radioactive. But in terms of uses, at the moment, we don't need to worry about them too much. Any information about those that you would need in the exam will be given to you in an exam question. So don't worry too much if we can't remember those. We then started looking at some of these electron structures, and what we said is there was a series of rules that we need to follow when we're putting electrons into our energy levels, shells, orbits, whatever we want to call them. So we said, I'm going to type this at the moment because actually it's a little bit quicker for me to type than it's to write. We said, so for electron, he says, configuration, we said that electrons, no, let's start that again. We said that each energy level, shell or orbit must be filled before moving to the next. We then said the first shell can hold 2 electrons. We said the second shell can hold 8 electrons. And realistically, that should be the second and the third shell. Okay, so those were the sort of basics and the sort of the rules that we have to follow whenever we're applying and we're putting electrons into configurations. And this is absolutely fundamental across foundation and higher. You have to be able to do the electron configuration for the first 20 elements. Now, hopefully, by the time we've been through this again, you won't need to remember any of them. You can literally look at the periodic table and work them out. If that's something you are struggling with, either ask questions about the bits you don't understand, or we can go through it again, but it just comes with practice. You can memorise them, but actually you're better off learning how to do these electron configurations, how to work them out from the table. Now, if you go on and do science at a higher level, you realise that actually these energy levels, there's a little bit more going on. We actually have sub-levels. So we have what they call S sub-levels, P, with the transition elements we have D, and there's other ones as well. And that's absolutely fine, and what you'll find is a lot of A-level students go, oh, you lied to us at GCSE. It's like, not really. The rules, even when you go to A-level, the rules still apply for the first 20 elements. We make a few changes after that. It's just we add more detail in so it becomes more accurate. But the same rules actually apply. And if you want to go through that at some point, no problems at all. I'm more than happy to do that. Now, what we looked at then is we started saying, and if I just take the first, let's do lithium, let's do nitrogen, and I'm just going to pick sulfur. Okay, and we'll just go through, we'll draw these out so we can start seeing, because we did lithium last time, we didn't do the other two. So we said that lithium has 3 electrons and 3 protons. Nitrogen has 7. I'm not worried about the mass because the mass has no relevance at all when it comes to electron configuration. And we said that sulfur has 16. So remember, these are atoms, so they have a neutral charge. And if they have a neutral charge, they're going to have the same number of protons and electrons. So atoms equal neutral charge. That's a 0 charge. So therefore, protons, which are our positive charges, equal electrons, which are our negative charges. And that's really important because it means that every positive has been cancelled out by a negative charge. Now, if we start drawing this one, I know that lithium has 3 electrons. Now, I can do this as a number exercise if I would like to, before I start drawing them out. I know that my first shell can hold 2 electrons. So 3 take away 2 is going to leave me with 1. I'll do the same for nitrogen, and then in sulfur I'll do it by drawing them out first. Nitrogen has 7, so my first shell can hold 2, that leaves me with 5. My second shell can hold 8, so I'm not going to fill that, so the configuration will be 2 and 5. Now if we draw these out, lithium, let's do nitrogen here, and we'll draw sulfur down here. And sulfur, you'll see, is going to need 3 shells, and you'll see why in a moment. So I'm not drawing anything in the nucleus because it's not relevant. When we're looking at nuclear science, we're generally looking at physics. Chemistry isn't interested in the nucleus. So I'm just going to put the symbols in here for the moment. It's going to make my life much, much easier. And as chemists, we really want to try and make our life easier. which is why we like learning the rules, because the more rules we can learn, the less content we have to memorize. And that's great, because it means we can actually do a lot more information without knowing as much, as long as we've got a good understanding. So I've got 3 electrons, 2 fills that shell, 3. I'm going to look at nitrogen, 2 fills that shell, that leaves me with 5. If you remember back to last time, I said that where we can, we're going to pair them up, because actually what we want to do is we want to make these really easy to count. We don't want to overcomplicate matters. We don't want to start spacing them nice and neatly out and run the risk of counting them wrong, because we've actually made sure they're all exact distances around the outside. Sulfur's got 16, so let's see how that's going to work. 2 goes into the first shell. That leaves me with 14. My next shell can only hold 8, so I'm going to fill that. So 14, take away 8, it's going to be 6. And however you space these out, that's fine, but I would suggest pairing them up. So sulfur, we've got 6. So the electron configuration will be 2, 8, 6. Now, going back to the periodic table, like I said, this is just a recap from last week, just to make sure that you guys are happy with this, because it's really, really important. Before we go on and look at ions, before we go on and look at chemistry 2 with the structure and bonding, if we're struggling with the electron configuration, it makes everything else so much harder. So let's just see how we could have used the periodic table as a bit more of a cheat sheet with this one, if we didn't want to work it out quite this way. Lithium is in period 1, and the group tells us the number of electrons in the outer shell. And that fits our rule all the way down. Lithium is in group 1, and I got 1 electron in the outer shell. Nitrogen is in group 5. I have 5 electrons in the outer shell. Sulfur must be in group 6, and sure enough, it is in group 6, because it's got 6 electrons in the outer shell. If we look at the number of shells we've got, that equals the period number. So lithium is in period 2, so row 2. So it's got these 2 shells. Nitrogen as well must be in period 2. And if I look at sulfur, sulfur should be in period 3, because I've got 3 shells that have been filled. And sure enough, it is in period 3. Okay? So we can use this very, very quickly to work out the electron configuration of anything in the first 20. If I take calcium, calcium got 20 electrons. I'm not going to work it out that way to start with. It is in it's in group 2. It is in period 4. So I'm going to have 4 shells. I know it's in period 2, so the last one's going to be 2, and I'm just going to fill the others. 2, 8, 8, 2. If I count these up now, 2 plus 8 is 10, plus 8 is 18, plus 2 is 20. That equals this number, so that's my electron configuration. I haven't had to draw anything out. I've not had to do lots of maths. I'm just using the periodic table to make my life easier. So spend the time with that, and if you've got any questions, please feel free to ask. But it's the sort of thing that you can practice at home. You can watch the video, you can choose any element in the first 20. Don't worry about anything after that, it won't come up in GCSE, but if it's something you want to learn later on, we can go through it at school. But going above the first 20 is definitely A-level. They might ask you the number of electrons in the outer shell for any of the main groups. That's fine. I can take Xenon here. Xenon's in group 0, sometimes called group 8. That's going to have 8 electrons in the outer shell. It's going to have a full outer shell. If I take iodine, iodine's in group 7. It's going to have 7 electrons in the outer shell. That's fine. I'm not writing down the full electron configuration for those. I'm just working out the number of shells it's got. Likewise for iodine, it's in period 5, so it's going to have 5 shells in total. But the other shells get a bit more complicated, so we're going to leave it at that. So if you've got any questions, do feel free to ask, but you've got to make sure that that basic information is sort of firmly rooted and that you understand it. So just because obviously I'm going to provide you with these notes, we're just going to put on here the period number is the number of shells or energy levels, depending on what you want to call them, for that atom. Okay. Now, the reason I've sort of gone through this and I've spent a bit of time just going through and recapping is the number of electrons in the group have a very important role when it comes to the properties of them. Now, if we go back and we look a little bit at the history of the periodic table, the only person you really have to know about in some detail is Dmitry Mendeleev. So he wasn't the first person to start grouping some of the elements. If you look back on Google and you start looking at some of the original sort of periodic tables, other scientists, sort of John Newland and some of the other scientists before him, they realised that that certain elements can be grouped together, they've got sort of similar properties. And as we start working out the atomic mass, initially they were grouped by atomic mass. Now, we didn't discover all of these to start with, but what they noticed is roughly every 8 elements the properties repeated. But there were some issues with this. What Mendeleev did is he came along and he said, well, actually, go back to the periodic table, he said, actually, when you look at these, some of the atoms that you have don't properly line up at the moment. So, for instance, you may have had boron, aluminium, germanium. Well, germanium didn't fit underneath aluminium. So what he did, and this was quite revolutionary at the time, is he said, well, actually, I think we need to be leaving gaps here. I think there are elements that exist that we haven't discovered yet. So he said, actually, there is an element that should go in here. I'm going to call it Eka aluminium. I'm just going to put AL for aluminium. Eka means one removed from. He came up with other ones as well. Scandium, for instance. He said there should be an element there. But what really set him apart is he didn't just say, actually, there's elements we haven't discovered. He actually managed to successfully predict the chemical properties of those elements. He predicted what the atomic mass would be. He predicted what the appearance would be, what the densities would be, and how they would react with other elements. And these hadn't been discovered. So he came up with these predictions. And of course, to start with, a lot of people thought they were slightly bonkers. I mean, how do you know they exist? But he used it by looking at the evidence that he already had. And actually, his predictions came true. They discovered that gallium did exist. It's now called gallium. So Eka aluminium existed. And all of the properties, including the density, the melting point, the appearance, that he predicted were true. And he did this with several other elements in the periodic table. So Mendeleev was very much a big player in putting it into a similar format to what we've got now. It wasn't exactly what we've got now, but it was very, very similar. Since then, we have changed the periodic table, and we've actually now arranged it in terms of atomic number. What they didn't know about, though, is they didn't really know much about the electrons in that time. So they didn't know about electron configurations in any way, shape or form, because if you remember when we go back to the last lesson and we looked at atomic structure, it was actually Niels Bohr that came up with a lot of the theories, a lot of the ideas, and a lot of the current information about energy levels and about orbits and shells. And that was after all this happened. So once we knew that, actually we can start seeing a lot of these similarities. So let's start looking at group 1. Let's go down here and we'll have a look at group 1. Group 1 we call the Alkali Metals. And as we've just seen, they have one major thing in common. They all have one electron in the outer shell. Now, I've said before that chemists are mainly interested in electrons. The electron configuration determines the chemistry and how things react. So, generally speaking, when most elements react, what they're trying to achieve is a full outer shell. Now, I'm not going to use words like happy and things like that, because that sort of seems to indicate that atoms are living things with a personality, and it's not true. What we're trying to achieve is the most stable configuration in terms of energy. So atoms are most stable with a full outer shell. And we're going to do a lot more of this when we go on to chemistry 2. But actually, they will achieve that full outer shell by either losing electrons, by gaining electrons, or by sharing them. Now, group 1 will all lose 1 electron in a chemical reaction to achieve a full outer shell. So if we sort of put down what we had before when we were sort of thinking about lithium, we said actually lithium has, and I'll draw this out again, we'll do lithium, I'm going to draw sodium, 1, 2, 3, and I'm going to draw potassium. Remember, I know how many lines to draw. Technically, lithium has all these other energy levels as well. It's not something that only exists for elements down the period. But lithium only has electrons in the first 2. Okay, so I'll just draw this one over here, just so you can see it doesn't make a lot of difference where I put the electrons, as long as I've got the numbers right. Sodium, we're going to fill up. And we've got potassium here as well. Just quickly fill these in. There we go. So they've all got 1 electron in the outer shell. So during a chemical reaction, all of these are going to lose that outer electron. What's going to be left is a full outer shell, because if you have a look at it, the next shell down for potassium is 8. It can only hold 8 electrons, so that shell is full. Sodium, if we lose this one, the next shell down is 8. It can only hold 8 electrons, so that shell is full. And if we look at lithium, lithium only has 2 electrons in that first shell, but the first shell can only hold 2 electrons because it's very small. So that shell is also full. So all of those become stable. Now, we said before that the definition of an atom, and if I just scroll up here, they have a neutral charge because the number of protons equals the number of electrons. Now, if I lose one of the protons and sort of recalculate this for a minute, we know that lithium has 3 protons. If I lose 1 electron, I'm only left with 2 electrons. So this is the same as saying I now have +3 and I have -2. If I add those together, my overall charge is +1. So I've taken away something negative, which means I'm left with something positive. I have 1 more proton than I do electrons, so my overall charge is +1. If I look at sodium, sodium has 11. Yeah. Just doubting myself there for a minute. Sodium has 11 protons. And normally it would have 11 electrons, but now it only has 10. Because I've lost 1 during a chemical reaction. So again, if I do the same maths, I have +11. I have -10. So if I add those together, my overall charge is +1. So you should start seeing, again, this sort of common factor here. The charge is the same. I do the same thing with potassium. Potassium has 19 protons. In the atom, it would also have 19 electrons. But when it reacts, it loses the outer electron. So it's only going to have 18 electrons now. 2 plus 8 is 10, plus 8 is 18. So if I add those together, my charge again is +1. So one of the other rules that we can write down when we're looking at group 1 is they all form a +1 ion. So remember, I've changed this definition now from an atom. So I'll come back to that in a moment, Tanishka. I've changed the definition from an atom to an ion because they no longer have a neutral charge. Right, so in this case, Tanishka, we are losing electrons, we're not sharing. The losing and sharing electrons comes in when in chemistry 2, mostly when we start looking at ionic bonding and covalent bonding properly. So we will come into lots more detail about that. We'll do loads of diagrams looking at lots of different metals. It's just, that's what happens to get to a full outer shell. So I'm going to come back to that when I cover chemistry 2 next week, which is what we're going to be doing next week. I'll probably even start it on Friday because we'll finish chemistry 1 today, most likely. So we'll come back to that on Friday. But in terms of losing and sharing, it's just to achieve a full outer shell. And what we've looked at here is all of these group 1 elements, and we've only got group 1 here. Group 1 elements all have lost 1 electron to form a +1 ion to achieve a full outer shell, because that is when they are most stable. And this happens during a chemical reaction. So I'll give you an example. If we leave sodium in oxygen, or even just in the air, sodium is massively reactive. And we'll look at reactivity in a moment, because that's what this is all to do with today. But if we put sodium in oxygen, it's going to react very, very quickly to form sodium oxide. And we'll have a look at why the formula is Na2O when we look at chemistry 2. But it's a very quick reaction. Now, if we take sodium to start with, sodium has, I suppose, properties that are very similar to most metals. If you had it outside of oxygen or with something that's not going to react, or in a vacuum, and you were to sort of have a look at it, the base element, it is still shiny. It would still be conductive. Maybe not as conductive as some other metals, but it's still going to be conductive. And we'll look at why it's conductive when we look at metallic bonding in chemistry 2. However, it does have some properties which is different from a lot of the metals we know about. If you think about iron, we build things out of iron, but you wouldn't want to build anything out of sodium. Sodium's soft. It's so soft, in fact, that actually we can cut it with a knife. It has a very, very low melting point. I'm just going to put MBT and BPT for melting points and boiling points. And these two we wouldn't expect for metals, but group 1 metals, and this is the same for group 1, all of them, they're all going to be shiny, they're all going to be conductive because they're metals, but they're going to be soft, and they're going to be having a low melting point and a low boiling point. Okay? However, because it's so reactive, as soon as we expose it to oxygen, we end up with a white compound in this case, which is sodium oxide. If we put it in water, and you need to know these reactions, if we put it in water, sodium's going to react with water very, very fast. It's going to form a hydroxide, so an alkali. Notice I said that they're all alkali metals. So in this case, it's going to form an alkali, and it's going to give off hydrogen gas. And that's going to be very, very reactive very, very quickly. So whilst we said sodium's shiny, we don't very often get a chance to see it as a shiny metal, because normally as soon as it's exposed to other chemicals, it reacts super fast. But yeah, if we do cut it, we can see it shiny for a brief period of time before it reacts. Now, all of group 1 will react in a similar way. If I look at lithium with oxygen, lithium's also going to react very, very quickly to form lithium-2. Now, I am going to cover balancing equations a little bit later on, At the moment, I need to do something about this as a chemist. This makes me slightly twitchy that I have a different number of electron atoms on this side to this side. So I'm just going to balance these out. But we'll talk about that in another session because we can spend a bit longer on that one. Likewise with this one, we can balance this out by doing that, 2, 4, and by doing that. So we'll just balance these out for the moment, and we'll come back to why that is later on. If I was to look at potassium plus oxygen, that's going to do exactly the same thing to form potassium oxide. Lithium oxide, sodium oxide, potassium oxide. If I was to do the same thing with water, the reaction is exactly the same for all of them. And even as we go down the periodic table, the formula's not going to change at all. So you are expected to know these equations. Now you can, for the foundation paper, you should only be able to do the word equation, but realistically, there isn't anything massively challenging about this, because once you've done one of them, the only thing that's changing in each case is the metal. I'm not actually changing anything else but the equation. So the reaction with oxygen is the same, the reaction with water is the same, the only thing that's changing is the metal itself. So realistically, you only need to learn 2 equations, the one for oxygen and the one for water, and then just change the metal. Now, one of the things we do need to look at is actually how do the properties, or how does this reactivity change as we go down the group? So if we look at group 1, we have lithium, we have sodium as we've already drawn, we have potassium, we have rubidium, we have cesium, and we have francium, which, so just go up, we can have a quick look. So working our way down. Notice francium has its atomic mass in these square brackets. That generally means it's got several isotopes and it's quite radioactive, so the mass is changing quite quickly. So we generally won't do anything at all with francium. It's difficult to get hold of, it's difficult to process because it's radioactive and it's breaking down quite quickly. Now, what we're looking at here is actually these ones, they become the reactivity increases as we go down the group. So working our way down, they become more reactive. And actually, if you look at the difference between lithium and sodium, lithium will sort of fizz around the top of the water a little bit. Sodium will generally fizz around and will often catch light. Potassium will go pop and you get a small explosion. Rubidium and cesium become even more impressive. And feel free to have a look on YouTube. There are lots and lots of videos on YouTube of people who have done this one. I was having a quick look actually before this session. I think, did I actually bring up, did I keep the video? No, but I can show you this very, very quickly. If I just bring up YouTube and we look up reactions of sodium. With this, there's lots and lots happening quite quickly. The lake's quite interesting when you look at that one, where they're putting some quite big lumps in. There was a guy, is it on this screen? Yeah, we can see this fairly quickly. We'll just open that up. Doesn't matter what's happening, but they start looking at different experiments that happen when you flush sodium down a toilet. So there's weird and wonderful things all the way through. This time they put a piece of wood in on top of the sodium. And let's just go back a bit. And we get quite an explosive reaction. So feel free to have a look around and do some research on this, and you can start having a look at the reactivity. Okay? It's quite interesting, but what's actually happening in these is, as with these metals becoming quite reactive, what's happening is they're generating so much heat when you put them in water that actually It's igniting the hydrogen that's being given off when the hydroxide is being produced. Okay? Now, a couple of notes that we can sort of put on here. These are all alkalis. It's worth noting that because it's the alkali metals. So they're all more reactive, and they get more reactive going down. Potassium is massively more reactive than sodium again. And if you look at some of the reactions with cesium in a lab, they will drop it into like a glass barrel, and it will actually shatter the glass barrel. Be slightly cautious if you look at the Brainiac videos. They've actually been enhanced with the use of explosives to make it look worse than it really is. It's not actually quite as bad as they show. They were actually rigged. They're still quite entertaining if you want to have a look at them though. So working down group 1, they become more reactive. They also become softer. They become much more easily cut. And the melting points and the boiling points decrease. Now, you should be able to talk about why that happens. So what I want to do is we go back up to these, and I'm just going to do that again. I'm just going to copy that really, so rather than drawing it out from scratch, I'm just going to copy and paste that in again. There we go. If I go back down there, oh. Is it going to work? If I go back down here and drop that in, there we go. We can ignore the rest of the notes, but this is quite important. Place the image. There we go. We can get rid of some of this for a minute. Right. The reason I've done this is we need to have a look at why they become more reactive. Because we're looking at it for group 1, I'm going to have a look at it for group 7. You won't need to talk too much about with the other, well, you don't have to memorize the other groups, but the similar principles occur. So with all of the metal groups, as we work our way down the group, the metals become more reactive. They become a bit softer and the melting point decreases. And it's all to do with how easily this outer electron is lost. So remember we said when they react, we lose this outer electron. So anything that affects the ease that that electron is removed is going to affect the reactivity. And there's two things going on here. If you think about the fact that all of the protons are in the nucleus, let's just get rid of, the, is it going to work? My keyboard's not working at all. So let's do it this way. We could think about the nucleus as being this positive area, okay? Because all the protons are in the middle. Now we know that opposite charges attract. So the outer electrons, in fact all of the electrons, are going to be attracted by that positive nucleus. So we've got this force of attraction. But if you think about the distance that outer electron is from the nucleus, as you work your way down the group, the outer electron is actually getting further and further away. So if you think about this in terms of magnets now, the further you pull two magnets apart, the less of the attraction between them. And that's the same thing that's happening here. So the further we get apart, the less attraction is felt by the nucleus. So the outer electrons are further from the nucleus. So there is a lower nuclear charge felt. Or we can put attraction. So, working our way down the group, outer electrons getting further and further away from the nucleus. So by doing that, it's feeling less of that positive charge, so there is less attraction, so the outer electron is more easily lost. And that's what we want to say. We want to say something about this outer electron being more easily lost. Now, I also said there were two things involved here. So it's not just the distance. As you work your way down the group, there are also more electron shells. So if we look here, we actually have more electron shells, or orbits, or energy levels. Each one of those shells slightly shields the nucleus and the outer electron. So we actually have an increased amount of shielding. So again, the amount of charge the outer electron's feeling, the amount of positiveness that it's feeling from that nucleus, has been decreased. So not only is it further away, there is actually more shielding, which means there is a lower positive charge felt by those outer electrons, so there is a weaker force of attraction, so they're more easily lost. And the more easily they're lost, the more reactive those elements become. Okay, if any of that is unclear, post in here. I'm more than happy to go through some of that again, but it's quite important you've got your head around this fact that actually, let's come up here, that actually as we work our way down, the outer electron gets further away, there is more shielding, so the outer electron has less, it feels the positive charge of the nucleus less, so it's more easily lost. So that's why it has these properties. So remember, we're always looking at sort of the cause and effect. We're always trying to look at linking some of these charges, and that's exactly what we're looking at doing here. So these happen because outer electron, and this is what you can put in the exam, outer electron further away, more shielding, less attraction, easily lost. Okay, we'll talk about density, we'll talk about getting softer a little bit later on, but that's quite sort of a fundamental here for what's going on. So just to recap for group 1 before I look at moving on, with group 1 we need to know they react with oxygen to form an oxide, and ideally we need to know the formula for that and the balanced equation. We need to know they react with water to form a hydroxide, and again we need to know the formula for the hydroxide, and I've just realised I made a mistake there. Let's just make that correct, that'll bug me otherwise, and I don't want you guys to get it wrong. There we go. We need to know the formula of the hydroxides and the fact that hydrogen is produced. We will look at the reaction with the halogens with group 7. I'm going to come on to that later when we look at the group 2s, or maybe even in a minute when we look at the halogens, because that's going to be the sort of the next bit that we look at here. So make sure that you're sort of happy with those and that you're aware of those, and that you can write them out. And you can practice that with any of those. Come back and have a look at your notes and see how well you did. Right, so let's just move over here and we'll have a look at the halogens now. So the halogens is another term for group 7. So without knowing anything else about these, I can make a couple of assumptions quite quick. I can make the assumption very, very fast that they all have 7 electrons in the outer shell. Now, to get to a full outer shell, they either have to lose 7 electrons or gain 1. And it's going to happen in the easiest way. It's going to require a lot less energy to gain 1 than it is to lose 7. So they are going to gain... Oh, let's do that there. Gain 1 electron to achieve a full outer shell. I've spelled that wrong. There we go. To achieve to achieve a full outer shell. And they're all going to form a -1 ion. Now, let's have a look at why that is. So, we're going to have a look at fluorine. So, fluorine, we know, is in period 2. We're going to have a look at chlorine. And we're going to look at bromine. And if we just have a quick look, if we just scroll back up for a minute. It's a periodic table. So we're looking at fluorine, group 2. Chlorine. We're not actually going to draw bromine. I'm just going to draw the outer shell for a minute, but it gives you an idea. Just so we know what's going on. Bromine is past that sort of first 20 elements. So we can't really draw it without learning some other rules. But we do know, without drawing all the electrons in, that it's going to have 4 electron shells. And it's going to have 7 in the outer shell. So let's go back in and let's draw this in. Right. Fluorine then. So, 2 electrons in the first shell. My next shell should have 7, because we said it's in group 7. And if I add these up, 7 plus 2 is 9. If we look at chlorine, we said that chlorine is, oh, that is a capital. I'll get absolutely shot otherwise, is 17. And if we look at this, 2 plus 8 is 10, plus 7 is 17. Now, bromine, we can't draw all of them. We know it should have an extra electron shell there, so I can put that in. But I'm not going to draw them all in. We're going to assume they're full. So I'm just going to draw the outer electrons in for a minute. But if you're looking at it going, well, it hasn't put them all in, that's because it's going to have 35 electrons, and we haven't learned the rules for that yet. So, if we have a look at what happens here then, they could lose all of these outer electrons, but actually it's much easier to gain 1. And we'll have a look at where those electrons come from when we actually look at Chemistry 2 on Friday. So, if we work out the charges here, we've got this idea that, so we have 9 protons. Remember, that's our +9 charge. But we're now, if we've gained 1, we're going to have 10 electrons. So if I add +9 and -10 together, I get the charge -1. Do the same thing here. I've got 17 protons. But because I've gained an electron, I've now got 18. So -18. -1. Okay, so we'll do the same thing for bromine. I have 35 protons, so that's +35. But because I've gained an electron, I'm going to have 36 electrons. Oh, hang on. Okay, so that's -36. So we add those together, and again we end up with a -1 charge. So when we're looking at the properties for these then, and we're starting to make these assumptions, and you'll see us start seeing a bit of a pattern going here. We have, so all of them, sorry, my shortcut keys for some reason have completely stopped working. They all form a -1 ion, they all have 7 electrons, and they're all going to gain 1 electron. Now, before I go through and just have a look at some of the properties of group 7, I just want to highlight a couple of facts of something else that we can use the periodic table for. So we've just said that actually, let's go for blue. We've just said that all of group 1 will form a +1 ion. We've said that all of group 7 form a -1 ion. We can put some other properties in as well, and hopefully you can work out why this happens. So group 2 will all have 2 electrons in the outer shell. They will all lose 2 electrons, and the ion they're going to form is +2. Group 3 all have 3 electrons in the outer shell. They will all lose those 3 electrons during a chemical reaction to form +3 ions. Group 4 we're not worried about for the moment. Going from the other end, group 8, and we'll talk about group 8 separately. Group 7 all have 7 electrons. They will all gain 1 electron to form -1. Group 6 all have 6 electrons in the outer shell, which means they need to gain 2 electrons to get to 8. So they're all going to form a -2 charge. Group 5 have 5 electrons, so they're going to gain 3 to get to a full outer shell. So they're going to form a -3 ion. So far, when we've looked at the periodic table, we said that actually the group number tells us the number of electrons in the outer shell. It also tells us the charge of the ion that is going to be formed during a chemical reaction. If we look at the period number, we know that it tells us the number of shells that's going to be formed. So I'm actually having to reduce the amount I have to know because the periodic table is giving me a lot of these answers. We said that going down group 1, they become more reactive because the outer electrons get further away, which means they're more easily lost. And that's going to be the same for group 2 and 3 as well. Let's have a look at what happens in terms of the reactivity of group 7, though. So, group 7 have to gain an electron. Let's just move back up a little bit more. It's about there. So group 7 have to gain this electron. And as we said before, the nucleus is this positive charge. So in other words, that outer electron is going to be attracted in by that positive nucleus. And in the same way as magnets, when you bring 2 magnets close to each other, they snap together. And that's what's happening during a chemical reaction. That outer electron is being attracted in, and it's going to snap into the correct orbit to fill that outer shell. So the more strongly it's attracted in, the more reactive it's going to be. So actually with this one, when we look at them, so we can put in, we've got fluorine, we've got chlorine, we've got bromine, we've got iodine, and we can carry on down the table. In this case, what we're looking at is they become more reactive going up the group. And it's for exactly the opposite reasons of group 1. So when we look at it, the reason it happens is because the outer electrons are closer to the nucleus. We have less shielding. So electrons are more strongly attracted. Okay, so that explains to us why it becomes more reactive. And if you're not sure, again, let me know. I'm more than happy to go through that. Other trends that we can happen going up the group is that we get an decrease in melting point and boiling point. And if you look at the properties of these and you look at the pictures, and I'll probably actually put some pictures up next lesson because we're nearly at the end of it today, so we'll do group 8. We'll look at the noble gases on Friday, and I'll show you some pictures of the halogens. But as you go up the group, you've got fluorine, which is a sort of yellowish, slightly coloured, very, very clear gas with slightly yellowish tinge. You end up with chlorine, which is still a gas, but it's a lot more green. Bromine is one of only 2 liquids on the whole of the periodic table at room temperature. So we're looking at 25 degrees Celsius. The other one being mercury. And it is a brown liquid, so the melting point's gone up. And then when you look at potassium, potassium. When you look at iodine, iodine is a sort of greyish colour solid. But actually, if you hold it in your hand, it melts or evaporates. It actually sublimes. You don't see it go through the liquid phase. It goes straight from the solid to a gas into a purple gas. So the melting point as you're going down the group increases. Going up the group, it decreases. Okay? Right. We are pretty much out of time now. So what I'm going to have to do is I'm going to stop there. Next, on Friday, because I want to make sure that we've got plenty to do Friday, what we're going to do is we're going to have a look at the noble gases. We're going to have a look at more of the properties of the halogens. We'll have a look at some pictures of that. I'll put some videos up as well to show you some of those as well. And we're going to start moving into chemistry 2, and we're going to have a start looking at ionic bonding. I also want to have a look at the transition elements, because we haven't mentioned those at all yet. And they're quite unique, and there's some quite cool properties of transition elements. So those are the ones between group 2 and group 3 in the middle. And a lot of the technology and industry and things that we have around us now rely on those transition elements. So we'll have a look at some of that as well. If I've confused you or lost you on any section of this, again, let me know, because on Friday, that's a great opportunity for us to go through and cover any issues. And I don't mind if you want to email me or message me or whatever. And I can come back to any of these topics and cover them, because having this base information now, having this really well-grounded foundation knowledge is going to make ionic bonding and everything else that we do, so covalent, quantitative chemistry, everything else we do is going to hinge on you properly, not just remembering, but understanding what we've been talking about on Monday and today. So I'd rather you drop me a message and go, yeah, you lost me, I haven't got a Scooby on this, so I can go back over some bits or break it down. Enjoy the rest of your day, and I shall see you Friday. Take care.